I am back. Isn't that exciting? This is going to be probably one of the harder ones. This is called probability of binomials. So, like the binomial probability distribution. Now, that sounds scary. I'm gonna do my best to make it clear for everybody. And also, somebody saw that I made a mistake back in 2-1. Obviously, I'm human. If you see a mistake or if you see any errors, what can you do? Just reach out to me. I'm more than happy to like try my best to explain it and make it better. Now, 5-2 is pretty tough. I was looking through it a little bit, but I want to just go through the book together really nice and slow. Then I'll pull up the notes page. So I'll share everything that I'll be doing for this one. So here we go. Here's the book. I'm going to be doing 5-2. This was the mistake I made, right? We're all human. But here are the notes. So I'm in Intro to Stats 5.2 binomial probability distribution. There's a lot of problems here. Obviously, this stuff is going to get a little bit easier, hopefully, as we go through it. But if you need me to make more stuff on like frequency tables, or if you need more stuff for like replacement, non-replacement, independent, dependent, just reach out. Okay. Just remember independent's like they're separate and dependent one follows the other. It's like you're replacing it. I mean, you're not replacing it, so it's changing the numbers. All right. So I'm in the book and let's get out of chapter 2. We're number 5 and they want 5-2. Why are we skipping 5-1? I don't know. But this is what's going on. As usual, I'm not changing the curriculum as it's been in place. I just want to try to make this as clear as I can for everybody. So 5-1 discrete probability distribution. The focus of this section is binomial probability distribution. Remember, bi just means two. Okay, so we're talking about like two different things at once. There's two parts. Methods for finding probabilities, easy methods, standard deviations, and things like that. As other sections, we stress the importance of interpreting probability values, whether events are low or very high. So this is the big piece. Binomial probability distributions allow us to deal with circumstances which outcomes belong to two categories: heads and tails, acceptable, defectives, survived or died. For you, our whole idea, because this is binomial, our two things are always accept or reject the null. That's what we want. Our two categories are always going to be like this was a successful study, a successful survey, or this wasn't. That is the main difference. That's why we're doing these binomial ones. So we have a fixed number of trials. So a certain number of ends or observations. The trials must be independent, which doesn't affect the other one. So these are all that are occurring without replacement, if that helps. I'm sorry, they're all occurring like if we were doing it with replacement, because each one's going to be separate because they're independent with replacing it. Each trial must have the two categories. So the only two options are yes, no, success, failure. Um, we've got a positive value or negative. This was a significant study and not significant. So, and the probability of success. So it doesn't change, right? So if it's going to be 99% accuracy, we need 99% for every one of the trials. That's what it means. So we've got some notation. So new notation. The probability of a success is P sub S. So it's a little p for a probability of success. Probability of failure, that's what this F stands for, 1 minus Q. That's probability of failure. N still number of trials. X is basically the specific number of N trials, so that X could be a whole number between 0 and N. So this is how many we've actually done it. So the X is the successes. P is the probability of the successes, Q is the probability of failure, and what we care about, P of X, the probability of getting exactly X successes in these N trials. So the one thing you have to remember from this, the main thing we're trying to get success, okay? That's the whole thing. So no matter how this shapes out, okay? We know we have either successes or failures, okay? So S is for success, F is for failure. Well, we want success. When they say the probability of X, this means the number of successful trials. Okay, that's what we care about. This is the one that means the most to us, is P of X of getting exactly X successes. So it's the probability of getting the successes out of that many trials. Let's keep going. Word success is used arbitrarily. Sometimes we want things to fail, right? Either of the two categories may be called success as long as it's n at infinite p. The value of q can always be found as q is 1 minus p. So if the probability of success is 95%, then q is 0.05. Remember, this whole idea of 95%, this means, because our alpha level for most of these, our alpha level, which is going to look like that, our alpha level is usually 0.05, and this means it's not. So this is 0.05, it's just due to chance. We got our answer due to chance. So this 99%, or like this 0.95, right? This means we're 95% sure it's not due to chance. That's the whole idea, okay? Let's keep going. When using binomial probability, we should always be sure that Q and P are consistent. So these cannot change. These cannot change. When an adult smartphone is randomly selected with replacement, there's a 0.05 probability that that person is cashless, never carries cash. Okay. Based on US Bank survey of 2003 adult owners, we find the probability that among 10 randomly selected adults, exactly 2 of them are cashless. Does this procedure result in binomial distribution? If this procedure does not result in binomial, identify the values of N, Q, P, and Q. Okay. So why does this satisfy it? Well, one, it's going to be the same thing. We still have this, basically this 0.05% for everybody. The 10 trials are independent because picking anybody, it's not affected by the results of the others. We're just using 10 trials. It's meeting all these criteria. Each of the trials has 2 categories of outcomes. So the selected person is either cashless or not, yes or no, that's it. And for the owner, we have this 0.05 probability that it's cashless out of the 10 selected people. So we can get all of our pieces, right? They wanted the pieces. What are the pieces? We're taking 10 people, right? We're taking 10 people. That's our N. Our N's going to be the 10 people. Sample's 2003, but our N is this. The people who we want is 2, so our X is 2. The probability, so the one that we want is 0.05. And the Q, what we don't want is 0.95. That's how the letters work. So let's find probabilities for getting X. First method involves calculation using this binomial probability formula and is the basis for the other 2 methods. The second involves using the calculator. So obviously we're going to do one by hand, and then we'll do some using the calculator. So let's do the first method. Here we go. We got factorials. All right, so I showed you this before. This is very similar to the formula I showed you before, but I'm going to really make this as clear as I can. When I showed you the NPR and the NCR formula. But this is the probability formula for getting X. N is factorial. That means all the numbers under N is factorial. And we have N minus X factorial, X factorial. And we're multiplying it by P raised to the X times Q raised to the N minus X. There's so much here, right? There's so much here. So we really have to think about each piece. These are our trials. These are a number of successes. This is the probability of success in one trial. and Q is the probability of failure. Now, can we use the one that we have? Yes, we can totally use the formula, the example of carrying cash for a smartphone or not. So P of X. Our first is N, how many trials? So we have 10 factorial, which we know is, well, I'll do one step at a time. And then we have N minus Q, so that's 10 minus 2 factorial. And we have 2 factorial. This is the combination formula. This is literally NCR that I showed you before. So this is N factorial over N minus R factorial times R factorial. This is every combination of choices. That's where this formula comes from. This is every possible combination of choices. And then we have to multiply that by the probability of it happening versus it not happening. That's where this formula comes from. That's how it's built. So this is just every possible choice. We'll do that first, okay? This is just what's NCR. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 10 minus 2 factorial is 8 factorial. This is what is, I'll use a different color. This is 8 factorial. And remember, this is just giving you all of the possible combinations. Now, when we also multiply it by the amount of groups, this means the order doesn't matter. This means the order of us getting these answers don't matter. So ready? Let's cross out everything that's a match. And what is 10 cut in half is 5. So our first number is just going to be 45, okay? Now, all we have to do is P to the X. So what do we want? We want 0.05 to the 2, right? So we have to multiply this by 0.05 raised to the second power. And then we're multiplying it by Q. And this is, so 0.05 is our yes, or what we want. 0.95 is our no, what we don't want. And so if we have 2 that we want out of 10, how many do we not want is 8. And this is going to give us our probability. So 0.05, sorry, 0.05 squared is going to be 0.025. 0.025. That looks weird to you. You could do 0.05 times 0.05. 0.0025. So it's 45 times 0.0025. And this is going to be 0.95 times 0.95. And we have 0.9025. There's that piece. There's this piece. And then we're multiplying it by, so remember, probability of it happening times the amount of people it happened with. Probability of it not happening times all the people it didn't happen to times the amount of groups. That's what each parts of these mean. So the amount of this happening for how many people? The amount of this not happening, the probability of not happening for that amount of people times every combination. That's how this formula works. So 0.9025 times 0.0025 times 45. So what is our probability? 0.10. It's 10%. We did it. So this is a 10% probability of somebody having a smartphone, not having cash in their pocket. I know that formula was crazy, but that's what all the parts mean and where they come from. I'll just reiterate this is the combinations. It's every possible combinations. This is the probability of yes, the probability raised to how many people it was, raised to how many was yes. Then this is the probability of no, that's your no probability. And this is how raised to how many people was no. If you put them all together, guess what? You will get your binomial probability. Now, I know that seems really confusing and a lot, but hopefully I'll do some more examples to show you exactly what that means. Ta-da! What a surprise. It has the combinations. The number of permutations is this, so the two sides of this equation are interchangeable. That's cool. Oh, so one side's combinations and one side's permutations. That's fun. I'm glad I showed you those before. All right. Should I do an example? Yeah, I might as well show you an example. Oh, I made a mistake. Guess what? Do we all make mistakes? I did 0.95 times 0.95 once, but we have to raise it to the 8th power. So I did this example. The only part that I missed was this last little piece. You know why? We're all human. So it's 0.09, sorry, 0.95 raised to the 8th power. So that's what this value is. This is 0.66342. And we can multiply that by 0.0025 and multiply that by 45. I squared this instead of raised it to the 8th power. And that's how we got the 0.07 or 7%. Guess what? We all make little mistakes. We want this rounded to 3 significant digits. Our answer is 0.0746. We times that by 100. It is 7.46%. So I had it right when I wrote it out. I just didn't put it right in the calculator. Calculation hit. Yes, you can use the NCX. Most calculators have this. And then we could also use technology. All right, so let's see how we can use technology to do this. As for binomial probabilities, the screen displays a list of binomial probabilities. As an example, 2. Notice that each display is given, and 2 is the one we do. Here it is. Okay. So let's actually use the technology to find it. We're not going to use StatDisk because we don't have access to that. I'm sure we can do it with Excel. It's not being my friend. All right. So the Excel gives us this formula. And we need to do a binomial probability. Okay, let's see. Let's see how this works out. Excel says 0 through 10, and it gives us these values. It doesn't really show us how. So I never used Excel for this. I've only ever used the formula. But guess what? Doesn't mean we can't figure it out. So let's go into Excel. All right. And let's see if we can go with data. We want a binomial probability. Do they have that for data analysis? Doesn't look like. Let's see how it works. To use Excel, it's equals binom.dist. Okay, cool. So it's just an equal to button. Nothing too crazy. Equals binomial dot dist. And I hit the parentheses. Okay, so the first one, the numbers, the trials, the probability of it happening, and then we have to say false. Okay, let's see if this works. So I believe the number of it happening is 2. And then we have 10 trials. Probability that we want this to happen is 0.05. And we want this to be, believe we want this to be true. But we're gonna find that out together. Let's see if I change this to false. See what happens. Oh, it is false. Okay, so binomial distribution, the first thing you have to do is put in the value. Okay, and then you have to put, so you have to put an X and then N, then what you have, and then we have to put, what's the difference between cumulative? I'm just gonna click on this. So if you click help, it should give you like some more information about it. The number of successes in trials, which is what we want. The number of independent trials, which is 10. The probability of success of each. Then, okay, a logical value that determines the form. If cumulative is true, returns the distribution of the function, which there are the number of most successes. If false, it returns it to the mass function that there are this numbers. Okay, so when we put true, true adds up. That makes sense, cumulative. This means it's adding up every single one before. So that's adding up 0 successes, 1 success, and 2 success. Now, if false, if it doesn't add them all up, we just want what happens when 2 people have it. That's what it'll do. So if they just ask you for a specific one that's false, otherwise it's true. But guess what? It works. Isn't that so nice? And here's your formula. That's a combination. Let me give you an example. I like it. I like it. So exactly 6. So if we wanted at most 6, if we wanted 0 through 6, we would put true at the end. That was easy. So let's do it again. So equals, the first thing we type is binomial dot distribution. The first thing that we type is how many successes we have, which was 2. I'm going to put 10 for the total. Our probability of getting it is 0.05. And then all we need to do is write false because we just want 2 being true and not all of them. If I could spell false, I'd be in business. There's our 0.074. All right, I hope that was helpful. All right, let's get back into this book. All right, we've got a football one. All right, let's look at this choice, right? I wish we had one of these sample editors. That'd be fun. But we don't need the sample editor. We're smart. All right, using the notation for binomial probability. Oh, sorry. In the chapter problem, we noted that 1974 and 2000, there were 460 NFL football games decided in overtime. 252 of them were won by the team who won the coin toss. Is the result of 252 wins in the 460 games equal to random choice, or is it significantly high? We can answer this question, which is equally likely. So we can try this. So if it's random, basically we can say it's 50-50. It's a 50-50 shot. Us what? Winning or losing the game. That's what makes sense. So to do this, all we have to do is just type this in. I'll use the Excel and see. So we have 252 wins, 406 games. Our P is 0.05. Sorry, 0.5 for 50%. And we just want to know if that makes sense. So let's see. Binomial distribution are the ones that we want. We're 252. And we have 460. And it's 0.5. And it's not and equal to, it's just for these, right? I forgot the equal sign. Binom. There we go. So we got 0.00454 is our answer. So they got 0.022. One was not practical here because we would need to apply it 209 times. We don't want to go there. 460. Two more wins by chance. Okay. There's another method. Nice. Well, we're gonna use the table and we're gonna look at this as well. But let's figure out where I made a mistake here. N is 460. Well, I could always just do it by hand too and see what happens. We can do it by hand and see what happens. So here's our formula. And don't worry if this is confusing. So n factorial. So we basically want p of x. So we know it's going to be n factorial, n minus x factorial. P to the x factorial. Sorry, I think it's p to the x and then it's q to the n minus x. Nice. All right, so we want to know for this this example. So we have how many games? We got 252 for the 460 games. So here we go. So our n is 460 factorial. And this is going to be 460 minus 252 factorial over 252 factorial. That's the first thing I'm going to do. I'm going to use a real calculator. Here we go. NCR is what we want. So NCR, so all I have to do is put our N is 460 and our amount of groups is 252. Nice. Notice that it already did it for us. Oh, sorry, 252. So 460 factorial, 460 minus 252, 252. That is not a small number. So I guess I got to do it all in one step. All right, which is fine. Times 0.5 to the 460. Times 0.5 to the, sorry, it's to the x. 0.5 to the 252 times 0.5 to the 460 minus 252. Close parentheses. So I have the NCR is what we want. That's the first piece, 0.5 raised to the probability of it happening, 0.5 raised to whatever is left. Maybe if I put some multiply signs here. Yeah, here we go. Nice, 0.5 to the 252, 0.5 to whatever this is. And it didn't give us a value. I guess it's so small, it didn't give us a value. Could be an error in the book, but that's pretty much what it looks like. This looks right to me. All right, let's go back to the book and see what they got. N is 460, P is 0.5, Q is 0.5. And we want to find the sum We want to find the sum of all the probabilities for each value from x to 252. Okay, so if we wanted all of them, the reason why we have a different answer is because I had to do what? Make this true, because we want all of them leading up to it. We want the cumulative. 0.982, is this what they got? Nope. All right, I'll just read the whole thing. The formula is not practical here because we would need to apply it 209 times. We do not want to go there. Table A1 of binomial probabilities doesn't apply because n is 460, which is way beyond the scope of the table. Okay, instead we chose to use technology. All right. The stat display below shows that the probability of 252 or more wins in 460 overtime games is 0.024224 rounded, which is low, such as less than 0.05. This shows that it is unlikely more wins by chance. We effectively rule out the chance. We are left with a more reasonable explanation that the team winning the overtime coin toss has a better chance of winning the game. Okay, let me think of one thing we can do. This is everything of it happening if we want this to actually happen, but we want the opposite of this happening. So what if I just take equals 1 minus the value? Nope, still off. All right, let's see if we actually have access to this stat disk. I want to worry about this one, obviously. Well, you can use the appendix. I'll show you how to use the table, but this one's not being our friend. I like how we got the first one right, but this one's not being our friend, even when we use the formula. Let's go. We're in chapter 5. Sorry. No, I want to go to StatCrunch and see if we can do this with StatCrunch. So we don't have access. The stat disk. Maybe we do. Let's see if we can find stat disk. All right, here's a binomial calculator. Oh yeah, we do. We have a binomial calculator right here. Okay, so let's see. We got standard, we got between versus standard. We want it to be everything less than this number. All right, let's use this binomial calculator with the values. So I'm in StatCrunch right now since Excel was not being my friend, and let me use our values. We know our n is 460. Okay, we know that our probability is a half, which is 0.5. And we want everything less than or equal to 252. Let's hit compute. 0.98211. I believe that's what I got in Excel. So Excel's giving me the same thing as this. Let's go from 0 to, unless I wrote the numbers wrong. 0.982. Okay, so I'm getting 98% either way for this one, whether I do this on Excel or if I use StatCrunch. So let's see if I messed up the numbers. It says 460 and 252. And we know it's 0.5. Not 0.05, it's a 0.5 probability. Let's try the top one, right? Let's do the one we just did with 10, 2, and 0.05, but we want it exact. Right, so let's try our stack crunch. Because they could have made a mistake. Everything's human. So this is 10. You just want it from, we want it basically from 2 to 2, and then it was 0.05. Yeah, so it works. Why is it 2 to 2? Because we just wanted a 2, 0.07463. That's what we got for this one. So I don't know. Maybe I just can't get this example, right? We're human. We all make mistakes. I can't figure this one out. Try not to hold it against me. All right, let's try to use the table and see what happens. Oh, there it is. Oh, so it is the 0.9821. 0.982106. Let's see. I just don't have that other part of it. So let's do, sorry, 252. I'm just looking around. Can skip past this, obviously. Okay, and this is 460. And this is 0.5. 0.982. Let's go back to the book. 0.982. I have X or fewer. And then X or greater. That's where the 0.17. So it'd have to, okay. So now I can figure out how to get the X or greater. Sorry that was so much. So how to get the X or greater, all I have to do is change this by one value, change this thing by one value, and then all I have to do is subtract it from 1. So if I make this, and then if we subtract it by 1, we should get the same thing. So it all works out. I guess I lost the book for a second, but it all works out. Sorry that was so confusing, but at least I got the right answer, which is what matters. I can understand why they want you to use this table version of it. So if it's 1 less, we have to change the value by 1, and then we have to subtract it by 1. So this is our 0.982. And if we subtract it by 1, we get this value, this 0.017. So the only way to do this is instead of using 252, using 251 and then subtracting it by 1. If I do that, I should be good. So the n stays the same. I have to change this to 251. Then I just have to take that value and do 1 minus the 0.971. And I got the 0.29 is what they wanted. Well, 0.02, yeah, and that's how we can get that value. So because we were here, we got this one, which is here. So if we go to instead of if we go to 251 and we drop it, then we get there. Oof, that was a lot. I would not recommend doing those, even with the technology, unless you have this specific program. All right, let's do this with this appendix A. Let's try appendix A. To use, all right. So this method can be skipped if the technology is available. So basically, if n is bigger than 8, or if the probability is not one of the 13 ones included. So you must first locate n, the corresponding value for x, and align the isolated value. Okay, so we just need appendix 1A. So based on the Gallup poll, 5% of adults are vegetarians. We randomly select 5 adults, find the given probabilities, find the probability exactly 2 out of the 5 are vegetarians, find the probability that there are fewer than 3 vegetarians. The following excerpt from table A1 shows that n is 5, p is 0.05, the probability for x is 2 to get it. That's how we can use the table to see where we are on it. Then we have to do 0, 1, or 2 if it's less, so we'd have to do all 3. All right, instead of using the table, we're going to use, we have the values. randomly select 5 adults. We can use this, so we can figure this out. Randomly selecting 5, it's 2. Let's just use stack crunch and see if we get the same values. So we randomly select 5 adults. We want to make sure we have 2, exactly 2, right? We go between 2 and 2, randomly selecting 5, and I believe they said it was 0.05 was for vegetarians. Yeah, 0.05 for vegetarians. So we should get 0.021. 0.021, ta-da, totally works. All right, now if I want from 0 to 2, I hit compute. Let's see. Well, we can do 0 plus 1 plus 2 if we want, but if we add all 3 together, it should work. 0.999, 0 plus 1 plus 2, or we can just put all 3 together. 0 vegetarians, 1 vegetarian, or 2 vegetarians, 0.99. So we got it. Yay. That makes me happy. All right. Part 2 is using the mean and standard deviation for critical thinking. The only one that was weird was the middle one. That's okay. Binomial distribution is a particular type of discrete probability, so we could use those same formulas, but if we know the values for n and p, it's much easier to do the following. All right, so the mean is the n number of terms times the probability of it happening. The variance is n times it happening times it not happening. And the standard deviation is the square root of how many terms it happening times it not happening. That's cool. As in earlier sections, this is mean, and that standard deviation can be great fun. I don't know about how fun it is. But here's a brief summary on the rule of thumb. So as long as we are what? 2 standard deviations away from the mean, lower, it's significantly low. 2 standard deviations above, it's high. And then not significant ones are in the middle. So, oh, we get this overtime problem. Let's do it again. 460 overtime wins. We get 0.5 and 0.5. For saying the coin toss doesn't find advantage. Find the mean and standard deviation of the number of wins for the 460 games. Use the range rule of thumb to find the values separating that are significantly low and significantly high. Is the result significantly high? So to get these values, right? We have our n, we have our p. All right, so these 3 formulas are actually pretty easy to work with. Right? Not the best with using all the crazy technologies, but these all make sense to me. So our mean, oh, I gotta reload the page. These are gonna be really easy to work with. Here we go. So our mean, remember, that's what mean is the n, which is the total number, and p is it happening. We have our variance, which is n times it happening times it not happening. And our standard deviation is honestly just going to be the square root of the variance. So if we have the pieces for this formula thing, we should be good. So our n, well, first let's get the mean. Our mean is what? Our mean is our n, which is 460 is our n, and our p is just going to be it happening. So what's half of 460? 230 games. Done. Our variance for this, sorry, our standard deviation for this is the square root of 460 times 0.5 times 0.5. So that's it happening versus it not happening. 0.5 times 0.5 is 0.025. So it's basically like, what is like a quarter percentage of this? So that's how you get the 10.7 games. But let's actually do it. 0.5 times 0.5 is 0.025, or sorry, just 0.25. So what is 1/4 of 460? Is 115. That's the variance, but we have to do what to it? We have to take the square root, and that's how we get the 10.7. So we just have to see if it is more than 2 away from the mean. As long as it's more or less than 2 away from the mean, it'll be extremely high. So I have to take the standard deviation and do what to it? I have to double it. I have to times this by 2. We have to be more than 2 away. So 10.7 times 2 is 21.4. Now, if I have 230 and I add 21.4 to it, I get 251.4. Is that 2 times bigger than the mean, right? That's basically our value. So we know significantly high is 251 and significantly low is the other way around, which is 208.6. Well, what did we get, right? What was the value that we got? Our value was 252. 252 is higher. 252 is more than 2 standard deviations away. Is more than. So 252 is greater than this number. That is why it's significantly high. All right, we don't need the rationale for the formula. They're doing the combinations again. Oh, can we just go to this Triolostats? Is it literally just a website? Oh, that's nice. I'm just seeing if I have access to this stuff. It's the mini tip. No, a stat disk. That is cool. So we do have access to that Triolostats. So I'm trying to download it. Sometimes it doesn't work because I'm using the school computer and they don't let me download anything on this. So I guess I could do it on my like home laptop. Yeah, it's not gonna let me open it. That's chapter what, 5? Oh, oh, that's with the data sets. Stat disk, will you work? Use stat disk online for free. Oh, nice. Okay, cool. Back and forth on this thing. I don't know. I'm sure you can figure this out. I want this guy, right? Dice generator. No, that's boring. All right. Stat disk for Windows is no longer actively supported, but can be downloaded here. Here we go. I'm pretty sure there's not a specific problem that you really need it for, but let's see if this will actually work. Nope, it's not gonna let me put it on here. All right, well, I tried. I tried and failed, but at least you guys can put it on your regular computers if you want it. I don't think I'm gonna use it. All right. we've made it to the end. Sorry this one was so long. Sorry I made a mistake and I had trouble with one of the problems, but guess what? We're human. We all make mistakes. This stuff usually has some stuff in it that's hard for me too. So I'll explain to you how to do all these. I'll make it make sense. And there's a ton of problems. I'll do at least half of them for you. Let's start with number one. Randomly selecting a character in a movie, the probability of getting a female is 0.331. Oh, inequality. If we want to find the probability that among 5 randomly selecting characters, there were exactly 2 females, we would use this solution. Oh, okay. Female times male times male times male times male. All right, so what is wrong with this solution? Oh, what is wrong with this solution? Okay, it's like, this looks weird. It's because it doesn't have the percentages here. So the real formula we want, if we want exactly 2 females, the formula should be what? So the probability we want 2, right? So we know out of 5, right? We're talking 1, 2, 1, 2, 3. Okay, so here we go. It doesn't account for like the differences in the probability. So it's n factorial over x factorial times n minus x factorial. We've got p to the x and then q to the n minus x. So here we go. 5 factorial over 2 factorial times 5 minus 2 factorial, and then I'll let the computer do it. The first one, what's the chance of getting the female? It's what's what we want is 0.331. We're raising this second power, and then it's q, which is the opposite 1 minus 0.331 raised to the third power. So we have this piece, right? We've got this piece. This is the end, but it's not accounting for all the different combinations that can happen. So that's the problem with the formula. But we can make this work. So 5 factorial is just 5 times 4 times 3 times 2 times 1, or 120. 2 factorial, and then we have 5 minus 2, which is 3 factorial. The first step I'm going to do, I'm going to cross out whatever's a match. And 2 goes into this, 4 twice. So this whole part is just 10. It's not accounting for the 10. It's missing the 10. It's missing all the combinations. So 10 times 0.331 squared times 1 minus 0.331 cubed. It doesn't have the combinations there. They're not asking you for the answer, but I thought I might as well give you the answer anyway. Times parentheses 0.331 to the second power close. And we're going to do times parenthesis 1 minus 0.331 close parenthesis, raise this to the third power, because that is what 5 minus 2 is for this one. Then I'm going to close that. And so the real answer is 0.299 or 29.9%. Ta-da! They didn't multiply this by 10, so that was their mistake. And that's the only mistake here. Yeah. They don't have the combination here. And the value they get is wrong at the end too. So let's see if there's anything else wrong with this. So without the combination, so they're not including that. So this is just one example where just the first 2 are female, the last 3 are males. They're not accounting for all these combinations. What do I mean? The female could be here, the female could be here, the female could be here, could be male, male, female, female. It's just not accounting for all these combinations. So that's the problem with it. And let's use this to make sure we got the right answer. So we have 5 and we want exactly 2, and we know that the probability is 0.331, and it's this 3.28. Did I make a mistake? I got 0.331. So let's go to Excel. We know we have what? We have 5. We want 2 females. And I want 0.331. And I want exactly that amount. I think it just has to be bigger. Oh, I have it backwards. That's why. 2 is what we want. 5 is the total. There's 5 trials. 0.328. This one got 0.328. So I guess I messed up with my math. Isn't that exciting for me? So me doing it by hand messed it up. Let's do a scientific calculator. Just do it on decimals. I want 5. NCR 2. I gotta put it here. Okay, so 5, 2, 10. I got that right. Okay. 0.331 squared is 0.109. Then I have 1 minus 0.331 raised to the third power. It's 0.229. So I have 10 times this value times this value. Oh, I think when I just typed it in or when I was doing it on the other calculator, I got it wrong. But guess what? It's right all across the board, 0.328. So I just showed you 3 ways to get it. As long as you don't make a mistake typing it in the calculator like I did, you'll get the right answer. Let's go to the next one. Assume we want to find the probability when 5 speaking characters move the ranks. Exactly 2 of them are females. Also assume randomly selected will be the probability of getting the. Oh, well, this is, we already did it, but let's see if we have to do, oh, it's 1 through 4. Okay. So we have everything here. So your N is what we want. So your N's your number of trials, which is 5. Your X is how many we want exactly, 2 females. Your P is 0.331, and your Q is 1 minus that. Just gonna use decimals from now on. 669. That's number 2. Again, assume that when we randomly selecting a speaking character in a movie, the probability of getting a female is this. Want to find the probability of 20 females when 50 different speaking characters are randomly selected from a population of 1,500 characters. Probably 20 females when 50 speaking from a population. 1,500 speaking characters. Are the 50 selections independent? Okay, 3 is tough. 3 is nice and tough. So for 3, let's not mess this up. Let's see, we just have to be more than what? We have to just be greater than this 0.05% for it to be independent, right? So let's do the math and see what we get. So now we want to find a probability of 20 females when 50 speaking characters. 50 randomly selected. All right, so I'm gonna go 50, 20. Let's see. Got 0.06 for this. So I looked in the back of the book to see what it said just for this one. They said in the back of the book, because 50 selections are made without replacement, they are dependent, not independent. That makes sense. They're dependent because they're not being replaced, the amount of women. Based on the 5% guidelines, the fifths can be treated as independent. All right, so let's see if 50%. Oh, all right, so it's just out of the population. So you don't actually have to do this part of the math because it's out of the 1,500. That's what they say you have to do. So if we're taking 50 people out of the 1,500, is this going to be less than 0.06? We got 0.03. 0.03. So this is usually going to be independent because we're not replacing the people, but because it's 0.03 is less than 0.05, we can't, it's going to be, we can treat this as independent. As long as we're less than this amount, we can treat this as independent. So both ways, it's going to be independent. The first way, all right, so the first way it's saying is dependent, right? Because we're taking them out of this population, so one depends on the other. But because 50 out of 1,500 is just 0.03 for the calculations independent. Wow, sorry, that was a lot. Let's look at 4. Using the same survey described in exercise 1. Okay, the probability of randomly selecting 50 speaking characters from movies and getting 40 females is expressed as 0 plus. Does 0 plus indicate that it's impossible to get 40 females among 50 people? What is the 0 plus? Let's see. So we're using this one, right? From example 1. One selecting 5 out of 2, we get this value. Okay, but now we're selecting what? 40 among the 50. So let's see what that gives us. It's so minuscule. The probability is just such a small number. It's almost impossible. That's what it means. The probability of this likelihood is almost impossible to happen because it's so off the charts. That's what it means by number 4. The 0 plus means it's slightly more than 0, but it's actually 0. It's almost impossible. That's what it means. Using this percentage, if only 30% of the time we get a girl speaking, and somehow we get 40 out of 50 of them lead characters being girls, it's like almost impossible. That's what this number 4 means. Let's keep it going. I'll try not to make any more mistakes. Let's look at 6 and 8. Learn whether the procedure can be treated as a binomial by providing the 5% guideline for cumbersome calculations. For those that are not binomial, identify at least one requirement that is not satisfied. Okay, so for all of these, you have to look at the satisfaction. Like so number 5, Number 5 is not wrong because it has to just be one or the other. It's got to be a yes or no. For number 6, it is yes or no. In a Pew Research 309, were asked if they ever fired a gun, and the responses consist of yes or no. However, it has to be like the same percentage for each. Pretty sure that's what you need for this, for your 5% guideline. We don't have enough information. There's like all of these things for it to be the binomial distribution, right? Is a fixed number of trials, which we had. Independent makes sense. Each trial must be categorized into yes or no, success or failure, and the probability of a success remains the same. We don't have that probability of the success remains the same. We don't have that specific probability. That's why number 6 is off. We don't have, wait, no, we do. It's yes or no. It's 50%. So 6, we do have it. We've got them all. So let's do it. All right, so it's a 0.5%. We have 390. We can apply the 5%. All right, so determine whether the procedure is binomial. It's yes. And for those that are not, identify what it is. So 6 is a yes. This is a 50-50 shot of it happening. We have 390 people. One doesn't matter to the other. So 6, everything's good about. Let's look at 8. Clinical tribal Y-sort method of gender selection developed by the geneticists was designed to increase the likelihood that a baby will be a boy. When 291 couples used the Y-sort method and give birth to 291 babies, the genders of babies are recorded. I think this one's true. Why do I think it's true? It's gender selection. Yes or no? We have 291. The genders are recorded, and it's going to be 50% each time. So I believe 6 and 8 are true. Let's look at 11. In a ComScore, 3,600 households were randomly selected without replacement. Without replacement. Okay. And we're asked whether the house has a smart TV. So the answers are yes or no with a smart TV. All right. I'm going to look it up, make sure we're right for the last ones. All right. We're randomly selected without replacement. Yes or no works, separate works, this all works, but this 5% means they're saying we don't have 3,600 is not all of them. We don't have as many people. So that's what they're saying the difference is. So the sample size of 3,600 is not more than 5% of the population of all households. So we can treat this as independent. That's what it means, but it is binomial. So all of these were binomial. All right, answer the questions designed to help understand the rationale for the formula. In insurancequotes.com showed that 8% of Americans have stolen from outside their door. Consider the random selection of 4 Americans. Use the multiplication rule to find the probability that the first 3 did not have a package stolen from their door, and the 4th did have a package stolen from their door. That is P, N, N, and S, where N denotes the package was stolen, and S indicates the package was stolen. Okay, so for ours, right? For ours, we want this specific order. We want this specific order, so that's why we don't have to use the full formula for 14. So we want in the specific order N, 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 S. So the probability for the first one is it did not happen. So 8% was not stolen. So it's going to be 0.92 times 0.92 times 0.92 times 0.08. That's how it's going to work out. Because like, if you look at the formulas here, all you have to do is multiply because we don't care about it tells us specifically about this order. It tells us specifically about this order because we just care about the 4th subject. So the probability of this happening is boom, 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 boom. So all we have to do is multiply 0.92, or you can do 0.92 times 0.92 times 0.92 times 0.08. So it's a 6% chance of that happening. Let's put this one. Beginning with this, make a complete list of the possible different arrangements of those four letters, and then find the probability for each entry in the list. It should be about this. Let's see if it's different. So we have N, N, S, N, N, S, N, N, S, N, N, N. Because we have the first one. Beginning with the one we just did. So we start with N, 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 S. So these are all the options. And we have to figure out the probability for each. This one's 0.06. If we're just moving these around, they're going to be 0.06 every time, I believe. I can do another one. I'll do the last one. That's a match, 0.06. Based on the preceding results, what is the probability of getting exactly 3 Americans who did not have a package stolen from outside their porch, and 1 American who did not have the package stolen from outside the porch? So does this change? Does this matter? Are all these the same? Does that make sense, or is this different? So getting exactly 3, are all of these together? Do they work differently? I'll leave this part for you. I really want you to think this one through and really try to see what C makes sense. Let me do one more of these. Let's do 17. %40 of consumers believe that cash will be obsolete in the next 20 years. Which number is this? 17. Find the probability that fewer than 3 of the selected consumers will believe that cash will be obsolete in the next 20 years. I'll do 15 and 16. So to do this, right? To do this formula, the first one is exactly 6. So we have 8 people, right? So we know that our N is 8, our X is 6. Believe it will be obsolete, so 0.4 is P, 0.6 is Q. So for this one, all we have to do, the first one is pretty simple. So we want exactly 6. So 6, 6, we've got 8 people, and our probability that we want this to happen is 0.4. It's 41, that's 4%. That exactly 6 out of this will happen. 4% chance. If you want to use this one, you'll see. So we want 6 out of 8. And we want what? 0.4 and false. 4%. Cool. Let's look at 16. Find the probability that at least 6. At least 6. All right, so at least 6. So that could be what? 6, 7, or 8. 6, 7, or 8. So we go back here. I want between 6 and 8 for this value, right? 6, 7, or 8. So now it's 0.049, which is what? 0.05. This is 6 people doing it, 7 people doing it, or 8 people doing it. The last one is fewer than 3. Fewer than 3. All right. So this one was at least 6, fewer than 3. So what is fewer than 3? We go here, fewer than 3 is 0 to 3. This is going to be a lot higher. Yeah, 60%, 0.59. Or what? I'm not going to round it, 59%. Cool. Well, I hope this was useful. I know these are hard. Sorry I had such a hard time with a couple of them. I just want to make this as clear as I can for everybody. I'm stopping sharing the screen. I know I did some extra ones. I know this was long. Just reach out if you have questions. This is probably the hardest chapter I've seen so far. The formula was crazy. The using exponential was crazy. So definitely reach out if you have questions.